All right, so let's go ahead and get started. It's starting to feel like springtime again in the wonderful state of happiness where we live in. And yeah, so I'm hoping that the old saying that the groundhog has seen the shadow is not true, and that we're not going to get more winter, but more warm weather like today. Anywho, so let's go ahead and get started with this. We're at lab 6, one sample t-test. And what we're going to be doing is combining some concepts and ideas that we looked at before. It's just going to be at a slightly different light. So we looked at z-scores and we've been able to track things down and how to get the percentile based on the z-score. And then we did hypothesis testing. Now what we're going to be doing is we will be looking at ways in which to calculate the reason for rejecting the null hypothesis or retaining the null hypothesis. So we're going to perform the calculation to make that justification. So yeah, the question is, how do we know when to reject the null hypothesis? And statistics is going to be to the rescue yet again. So let's say we have this population of people in Massachusetts, and we take a sample. What we're going to be doing with one sample t-test is we're going to be comparing a population mean to a sample mean given a treatment. In our previous example, we looked at one group of participants receiving marijuana and another group of participants not receiving marijuana, and then we're seeing testing differences between their artistic performance. In this case, we're taking a sample of the population and we're just giving that sample that treatment and seeing if there's a difference between the overall population and that particular sample. So we're going to be looking at alpha levels, and that's going to set our criteria of whether or not to reject or retain our null hypothesis. And these alpha levels are corresponding to cutoff regions or critical regions. Now, the question is, what is a legitimate cutoff region? What is a legitimate alpha level? Well, the standard in the social sciences, what you'll see time and time again, is alpha level, which is determine the set point of whether or not you reject or retain the null hypothesis. It's set at 0.05. So that's basically saying if there is a less than 5% chance that the mean of one group is equal to the mean of the other group, then we can reject the null hypothesis. If it's 5% chance or more, then we can accept or retain the null hypothesis. Now, here is the critical region. Right here, we have a relatively normal distribution, and we have this cutoff region right here. Now, anything to the right of this cutoff region will be determined as a statistically significant difference between groups. There is a difference between a population mean and a sample mean given the treatment. And so that's going to be our indication here, is we have to have a value that is in this area of the critical region. Here's the cutoff zone right here, and here's the critical region in pink. And here is the non-critical region. Now, if we get a value or a t-statistic that is in this region, and I'll talk about t-statistic a little bit later on in this discussion. If we get a t-statistic in this region, then we can retain the null hypothesis. And so that's pretty much how this is going to go. If there's a less than 5% chance that the null hypothesis is true, then we reject the null hypothesis. More of like in layman's terms. There's more technical terms to it, but as we're learning these concepts, we're just going to kind of use more of the common terms to relate to these ideas. And here are them together, non-critical and critical region. And if it passes this cutoff zone for, I should say, a one-tail test, it's going to have this cutoff zone. And there's just going to be one concentrated area for one-tail test. And I probably should mention this right here. So I'm going to just write this down as I go, because I think it's just important to kind of make these corrections as we go. And it really emphasizes the point. I'll just say one-tailed. All right, so that's a very important distinction, because now we have a two-tailed, and with two-tailed, you have two critical regions and two cutoff zones. And it's still alpha level 5% or 0.05. So if there's a less than 0.05 alpha level, that there is going to be a that the null is true, then we reject the null. And let me say that again. If we have a less than 5% chance that the null is true, then we reject the null. And in this case, if we have a two-tailed test, we divide this by 2. And in this case, I'm going to make this red. We're going to divide this by 2, right? That's going to give us 0.025 on this area and 0.025 on this area, or 2.5%. All right, so let's go ahead and move on to this other concept. Hopefully that's clear, and this is how it would look if we had a perfectly normal distribution. We have 95% of scores in a non-critical region, and then 2.5% in this region and 2.5% in this region, and this is for a two-tailed test. Now, just to sort of visualize this a little bit, if we were to retain the null, this is what our sample population, sample population mean would look like. If we were to reject the null, here's the rejection region right here. This is what our sample population mean would look like if we were to reject it. And there's an 8-point effect, or 8-point difference between this group and this group when it comes to the means differences. And when we're looking at one sample t-test, we're looking at the differences in means. And if I was to illustrate this, here is the rejection zone in red, right? So once you pass this area, then you have a, you can reject your null hypothesis. You can say there is a statistically significant difference between the population mean and the sample population mean given the treatment. Now let's say I was to move this down over here. Once this passes this cutoff zone right here, and there's only 5% overlap, I believe that that's meant, or that's illustrating that we can reject the null hypothesis. But it has to pass that point, and I think we'd have to be essentially right here to pass that point. If we're right here, no can do. We're still, we have some, maybe this is about 7% instead of less than 5%. Maybe this is 10% rather than less than 5%. And then maybe this is at 5% and we want it to be a little bit more, right? So less than 5% overlap. And you can see it here at this side of the tail as well. All right. So now, here's just some of the scientific language. You can pause this and write this down or take a screen capture. I'm going to move on because the walkthrough does a really good job of illustrating this. And I probably should mention this too. In regards to the walkthrough, if we were to go to that section, let's see here. The walkthrough specifies some things that are very, very important. We're heading into hypothesis testing. It's time to walk away from z-scores and go into t-tests. And that's what we're going to look at when it comes to calculations a little bit later. Specifically, the standard deviation needed to be calculated, calculate the standard error for a population is not always available. So we will use estimated standard error associated with a t-distribution instead. So we're going away from the z-distribution, but it's the same concept, but we're going into the t-distribution to figure out if there are differences between the population mean and the sample mean, which is supposed to represent an illustration of the population, at least in theory. By calculating the estimated standard error, we can now plug in the value into the formula for t-statistic. So this is what we're going to be calculating in order to see whether or not we can reject or retain the null hypothesis. And so let me go ahead and move on to these slides here. And this is also important, I suppose, that you can have an alpha level at 0.1. Maybe that would be the set off zone when it comes to whether or not to accept or reject the null hypothesis. And that means that you would have to have a less than 10% overlap between the null and the alternative mean distributions. So this is what I was just talking about in this walkthrough right here. I'm going to go ahead and just make this a blank screen again because it's just too much information right now. All right, so we looked at z-scores, and now what we're going to do is we're going to make this calculation of a t-statistic. And that's basically a similar concept. We have our mean, our sample mean. Instead of using a data point, we're using our sample mean, and then we're using the population mean, all divided by this guy right here. And what is this guy? Let's go ahead and break this guy up into pieces. But before we do that, this is sort of the definition of t-statistic. We have the t-statistic is used to test the hypothesis about unknown population mean, and this should be a mu. So I probably should write that right now. Let's see, how am I going to write that? Give me a second as I pause this. All right, so I was able to do that and find the symbol for mu when the value of the s is unknown. This is the standard deviation for the population is unknown. So the formula for t-statistic has the same structure as a z-score formula, except that the t-statistic uses estimated standard error in the denominator. And the other difference is this right here is we're using our sample mean, sample population mean, and subtracting it from the population mean. And then yes, this is an estimated standard error right here. And if we were to kind of look at this, what we have here is our standard deviation divided by the square root of our sample size in order to get this. Just a very quick, simple calculation. Make this calculation, and then you put it at the denominator area of this particular equation. Now we have these two things, and I'm just sort of emphasizing this point that this is going to go in the denominator. And now we have things that we can say about the null and the alternative hypothesis. So really, I've seen this written in various different ways. This could be the population mean and the sample mean, or you could write it as mu as well, and maybe just designating this as population and this as a sample mean. But as the walkthrough has illustrated, we're going to use capital M, but you can also use mu as well, because theoretically we are using this sample to estimate or make inferences about the population. All right. So we have our null hypothesis, population mean, sample mean, and our theoretical population mean is equal to our sample mean. That's basically what that's saying. And then here's the alternative hypothesis. Not going to go into that much detail. We're going to also do calculations, simple calculations of degrees of freedom. It's just sample size minus 1. And we're using the t-distribution. So I think what I'll do